folks. This is Green Arrays' technical presentation for the afternoon. And my question is, how many of the folks in the audience remember Robert Anson Heinlein and his famous acronym, Tonstoffel? Show of hands. Alrighty. There ain't no such thing as a free lunch. Sounds like a law of thermodynamics, doesn't it? Probably is. But at any rate, the nature of this experience with Tonstoffel grew out of App Note 2, which in its most recent instantiation documented the method and energy requirements for exciting high-frequency crystals like 10 megahertz and up, as well as the watch crystals we'd run before. Now, at the end of that, we postulated, well, you know, it might be that we could run an RC time constant network outside the chip as a really low frequency, very long time delay, mainly for remaining situationally aware. It's no good for timekeeping. Well, it's probably, no, it's not as good as a sundial. The sundial doesn't integrate errors, does it? So, no, it's a crappy way to go away for a while and then come back and see what the heck's going on. And that was the general idea. And the arithmetic indicated that that would only cost us a couple of microamps to do while it was charging and discharging the RC network. And so it was probably going to be fun, and we finally got around this week to doing a little experimentation with that little concept. And the result is Tonstoffel. All right, the principle in question, the goal is to sit here with something looking very much like one of our pad drivers. Each of these power FETs looks like 20 ohms. Yeah. Let's try and drop right here. 20 ohms in saturation. So there's not going to be a lot of loss in those guys, especially since the currents are going to be vanishingly small. And then we go out here, and in this particular case, we're running a 10 megohm resistor into 100 nanofarads. All right, so the time constant of this whole circuit here is about 1 second, right? And so we would expect to cross our switching thresholds in about that period of time. So what we do is, this is node, say, 708.1, and we take and sample this to node 708.17, and we turn this guy on, let it go high, wait for it to cross our positive switching threshold, say cool, then turn around and drive it low to take it to the low switching threshold. Seemed like a good idea to both Daniel and me, because if you've got VDD of 1.8 and ground here and 0.9 here, our switching thresholds are like here, about a half a volt total range. And so what we would be doing is driving the thing up to here and then down to there and then up to here and down to there again. And that seemed like a good way to do this, to keep more or less a continuous time series without having to run multiple of these and find a way to time the discharge procedure. And so that was the goal, was to act like this. Well, we did. And we looked at the nice friendly Keithley, and it said that we were burning about 70 microamps, not 2 or 3. What the heck? The leakage of this particular chip was running about 13 microamps. So we were looking at a fairly substantial, like nearly 60 microamp cost to running that little oscillation of the RC in between the switching thresholds. Why? Ha! Tonstoffel forgot that it is not without cost to perceive things that move slowly in our chip. Look what we've got here. We have essentially negligible leakage on the order of 200 to 300 megohms on our input structure, so that isn't it. And our capacitance is only 2.5 puffs. Again, negligible compared to that. So what the heck was the problem? Well, the problem is this. Forgot all about our nice Schmidt triggers on the input. And if we're running the signal continuously between the thresholds, the hysteresis bounds of these guys here, they're constantly conducting. The Schmitts are that way. That's just how Schmitts behave. The peak current was like 120 microamps for these Schmitts when the input voltage is right at the center. And it tails off on both sides. So here is this nice distribution of current consumption by these guys as we vary the signal right there in that range. So there is where our 60 microamps cost of these guys perceiving the slow-moving signal coming in. And just to prove that it didn't get much better if we instead ran two different RCs, one of which went like this, and when we got up here and triggered, then we would drive this guy low. We would wait until he crossed the negative threshold. Then we would signal another node to start doing its guy and doing the same thing back to us. That way we at least gave this RC a head start on getting toward ground before we started driving the other one up, which would tend to keep these guys going between ground and the switching point rather than hovering in between. And in fact, if we didn't wait for that, we discovered that we did hover in between, and we were burning more like 120 microamps. But when it was all said and done, the energy consumption of this strategy with two nodes and two RCs, same deal, 60 microamps of current average. That's being averaged by the Keithley with a 10-second average, which is a pretty stable way to measure this type of thing, we found. So at any rate, bottom line is, Tonstoffel. Doesn't cost anything to drive it, but it costs a hell of a lot to receive it. So the next experiment that we'll do for low frequency stimulus for situational awareness is to see if it actually takes less energy to run an external CMOS timekeeping device. There's one we've identified that claims to run 100 nanoamps as being its claimed continuous power. We'll find out what it costs when it's actually stimulating us, and next year we'll document that just for laughs. It's certainly not going to be 100 nanoamps. That's not in the cards because it's going to cost it something to stimulate us, and of course they never brag about that in the data sheets. They brag about what they're doing when the chip is sitting there all by itself doing nothing of interest to anybody. We'll use the SPI one because SPI is more power efficient than is I2C in general, especially if the people have pull-up resistors on their drivers and drive them open collector or open drain rather than driving them push-pull. So that is the outcome of this little experiment. It's it'll warrant a footnote in that note too. But anybody that was hoping for us to be right about this, nah, we're wrong. That's too costly. You can't run slow-moving inputs and get away with it. Right? Moving to the bench, here is the setup used for running two of them. The one on the right is being driven by node 8. The one on the left is being driven by node 708. Both of these are 10 meg, 100 nanofarad RCs, and we're of course using a 1 ohm shunt resistor here to measure current used by that chip. All three of its power supplies are being driven by through that single resistor. The Keithley is connected across the resistor to get the voltage drop. Here is a trace currently running, and this is being driven by a pin off of node 8 that is being driven in sync with its drive to the RC. You notice that it drives the RC for about 580 milliseconds, and then it drives it to ground, and during that longer low period we wait for it to come down to the lower threshold. Then we send a signal across to node 708 to do the same thing, waiting for node 708 to send us back a signal to tell us to go again. So we've got a total period of this cyclic thing of 2.5 seconds. And here is the current being used, and that is reading 74.5 microamps with this lovely voltmeter. 74.5 microamps. That's a 10-second average again. So there we are. That's what we've learned with this little exercise.